fault-tolerant quantum chemistry.
So yeah, good morning. Thanks for all the people that made it out of bed. So if you remember one thing in this talk, it should be this slide, right? You should never, ever, ever approximate a controlled arbitrary angle rotation as the same as a controlled C0. Okay, it's nonsense, complete nonsense. Very hard to do anything continuous, especially hard to do anything continuous with error correction. As soon as you try, well, you have to take your arbitrary angle and approximate it with the rate one sequence of discrete gates. And this is not going to get a lot better, all right? This is what we now have after a lot of years of research and a lot of progress, particularly in the last 18 months. You're not suddenly going to wake up one day and find they are actually comparable. Okay? So, what we're going to do is take a quantum chemistry algorithm, which involves a lot of these controlled rotations, and really pull apart this common statement that we only require a few hundred qubits, to show that that's really not true. And you really shouldn't say that. So what's the problem? The problem is we want to find the ground state energy of a molecule. So imagine just taking all the electrons and nuclei of some molecule, spreading them out to infinity, pulling them together, and seeing what amount of energy is liberated, calculating that number. Now, you can argue whether that's useful or not, but it turns out that for a big enough molecule, that's very, very hard to do. So we're going to pick a molecule where it's classically intractable at the moment, and maybe for a while to do, and to see how much we need to actually solve that problem. And we'll break it down step by step until we have finally a real number of days of computation and a real number of physical qubits, and all the assumptions that go into getting those specific numbers. So the problem in a bit more detail. We care about this approximation. So we fix our nuclei in space. We leverage a whole bunch of quantum chemistry spin orbitals. So this is important. Someone has spent a lot of time on a classical computer already making highly accurate basis states. And then we use the following Hamiltonian, and this is essentially creating annihilation operators to work out essentially the lowest valued eigenvalue of H. And we do that by using a Trotter expansion of our Hamiltonian and iterating for some number of iterations that goes as 1 over the precision we desire. So there are still quite a few unknowns in this process, largely because we don't have a quantum computer. It's very hard to predict just exactly what the error rate will be when we run for a certain number of iterations. The best, I would claim, in the literature are estimates, and we still need to work on that. People are not even really sure what accuracy wants, let alone how many iterations you need. So there will be a certain amount of ballparking, but I will flag that when it occurs. So what does one of these terms look like? So this is taken from a paper with Matt Hastings and Dave Wecker on the list of authors. And this is one of these 4 variable Hamiltonian terms. There are a number of these in the sum. And you can see it decomposes into a lot of C0 gates and what look like quite a few of these blurry controlled rotations. All right. And in fact, there's quite a lot more Clifford gates than controlled rotation. So you might be forgiven for thinking, oh, we really need to care about Clifford. But keep in mind, one of these guys is over 4 orders of magnitude more expensive than one of these. So despite the fact there's 100 times more of them, there's still less than 1% of the total volume of stuff that you need to do. They're completely negligible. So one of the biggest approximations in this talk I need to make is that since we don't have a quantum computer and don't really know how long we need to run these things to get a good enough accuracy, all I've been able to do is poll a bunch of people that work in this field. And the current estimate is that you need about 10,000 quantum steps. So that could change, but that's the best we can do right now. So this converts into this, about 7.4 by 10 to the 10 control rotations. That's really what we need to focus on and implement and see what that means. So for a start, I was asked by a guy who actually works in quantum chemistry, well, come on, let's just assume I have one logical qubit for each of the abstract qubits in my algorithm. How quickly can I do a logical gate? The answer is you can't. You can't do logical gates at all. If you have no ancillas, you can't prepare the states that are required to drive quantum computation. The speed is 0. Right? If you have one ancilla, you still can't do it. You actually need about 30 ancillas before you can even do any computation whatsoever. And in practice, you want a lot of ancillas to drive the computation quickly because quantum chemistry circuits are extremely deep. And if you don't optimize for time, they start taking years and years and years to run. Even what we do here, as we'll see, takes a number of days to run after optimizing for time.
Also, can you explain a little more? Is this a controlled evolution? Is that what is the circuit?
So this corresponds to one small step in the Fowler expansion. So this is essentially one of these guys. So the angles are small. So in the circuit, the control rotations here are small. And this is just a small step.
So what's determining the width here? Is this the number
So
of bits I
this
need
is
to
the
represent?
number of spin orbitals. So we're going to study FP2S2. It's 112 spin orbitals for the basis we're going to consider. And then one extra qubit for actually measuring the phase angle. So it's on paper itself, a 113 qubit algorithm.
So these are not single qubit lines that are drawn.
Well, in quantum chemistry they are, right?
But that's
But of course,
about
physically.
10 qubits, not 100 qubits.
Okay, so this is a schematic. So sometimes these, so wherever you see blank,
There's
there's
blank.
potential extension. Wherever you see this blank, there's potential extension. So yes, this PQ and RNS are a selection of 112 qubits. Yeah, 4 out of the 112. It's a generic set. Yeah, in general, you will notice that I've said there are 100 times more pivot gates than there are more rotations. So you have to scale this up to a circuit that's about 100 times. I'm sure you get the idea. So, implementing a controlled rotation. Firstly, we can't do this directly at all. You have to split it into something you can do. And you can use this nice little circuit to make a controlled rotation a pair of single logical qubit rotations. But then the expensive bit happens. So we don't have continuous rotations in our set of gates. We have to approximate them using sequences of Hadamard and TNT data gates. And we can do this optimally now. So optimally means it's not going to get better, right? There are a few tricks floating around that I'll talk about at the end that are different to this, that maybe get better. But I'm actually not that hopeful that they'll have much. We've already looked at a couple, one published, one not, and it's really tough to do better than this. So what is this? This is saying that if you want to approximate an arbitrary angular rotation to an epsilon, then you need, on average, depends on the exact angle as to what exactly you need, but on average, you need this many T-gates in a sequence of this form. So, firstly, the question is, well, how closely do we need to approximate these rotations? So, we know that we have a number of rotations, single qubit rotations, that is twice by this circuit, the number of control rotations. So now we have 1.5 back into the 10 single logical qubit rotations. And what we're going to say, which is an assumption, because we don't really have a computer, so we can't run these algorithms, but it's a reasonable guess, is that we only need a rotational accuracy. This is a rotational accuracy, not a probability of error. Okay? Within 1 on the square root of this number. So what are we saying when we do this? Naively, when you do these games, usually you go 1 on the actual number, okay? Which you think is a probability of error. So if I do 10 things with probability 1 on 10, I should have a good chance of getting success. Here I'm saying 1 on the square root because we're off by a small rotation angle, and so the actual overlap of these two is very high, with the error being the square of this. Okay, so we can go 1 on the square root. And when you do that, you find that you need sequences of this form, HFT, with approximately 53 T-gates. Yeah?
Why do you mention that you cannot do a single qubit gate in a continuous way, because you need fault-tolerant gates. Because suppose you have a two-level algebra, you apply just a microwave driving or with a laser and continuous driving, you can perform any intermediate angle.
Sure, but that's a physical gate, not a logical gate.
Yeah, so these are fault-tolerant gates.
Yes, these are logical gates. Error corrected down to whatever precision you want. That's the key difference. As soon as you turn on error correction has to have a discrete set of gates, because if it didn't, how on earth could it know what you actually wanted? There's no way. You have to have a few discrete points in your unitary space where error correction pushes you towards those points. Continuous is not possible.
But then how you handle the errors when you, because at the end this is meant to be physical, and when you do it physical, then it's time, finally time. And how can you control the errors in between?
So what type of errors are you talking about? There are many types of errors.
No, what I mean, any what you call a logical gate is, let us call it a frozen gate. It's a mathematical operation. But when you implement it, it takes a time. You see,
The duration of a gate, from the point of view of someone like me, is irrelevant. All that matters is the gate fidelity. So what are you asking?
No, that's exactly the answer I want.
Yeah.
So for you, it's just this set of gates that you define what matters, right? And then an experimentalist would have to provide you with that set of gates with the highest possible fidelity. So
that's right. I mean, we'll talk about gate durations, but the only thing gate durations do is make the algorithm take longer or less. For the purposes of error correction, and indeed any computation, classical or quantum, it ultimately comes down to error rate. Duration of gate should be tuned to minimize the error rate.
Is NT the number of single qubit operations or just the number of keys?
So NT is the number of T gates, because the Hadamard's plan per single logic.
Because typically you need thousands to do the single qubit part, right?
In the parts.
Okay.
So for those that are looking at this number and thinking, hang on, that must be way too small. This is what's happened over the last 18 months. So people have taken algorithms that used to run on this number to the fourth power and brought it down to the first power and proved a whole bunch of beautiful theorems that this is good. Yeah, but just imagine what slave one would look like if it was logged to the fourth power. Right? But no, it's much better than that now. So another thing I get asked very, very often is how long does a logical CMOS gate take? And the correct answer is no time. And then they say, no, what do you mean? It must take some time. No, it takes no time. So it's because it's a qubit operation. It's a very computationally trivial thing to do, and you can do it completely offline. So it does take resources. It takes space, time, and volume, but it does not slow down your computation at all. Zero. Because you can do this. You can do an arbitrary qubit circuit. Then you can do a T-gate, that's this dashed box. Then what you can do is this circuit here, this pair of CMOS. And what this is selective destination teleportation. I can take my state, and my state is, this is really a single logical qubit circuit. The input is up the top. I can take that, do a T-gate of it, and then selectively teleport it to here, or here. If it's teleported to here, I'll put it through an S-gate. So this is the correction for my probabilistic T-gate. It's really T or T-gate, 50-50 all the time. So I have to do this correction half the time. But no, I actually did it in the past. It didn't have to slow me down at all. So based on this measurement, which tells me if I got T or T-dagger, I then choose to do one of these two banks of measurements. And these are logical measurements, but you do a logical measurement using transversal single qubit measurement. So it takes exactly the same amount of time. So the only thing that limits the speed, and note, this is a whole algorithm. I can take any algorithm at all, and write it as a layer of Clifford, then a layer of T with a cricket escape, and then another layer of Clifford, layer of T, cricket escape, and so on. The whole algorithm in one flat level. And the only thing that limits how fast I can execute the algorithm and get the answer I want is this cascade of teleportations. And that's really the speed limit of quantum computation, not, oh, how long does a T-gate take? That's not the right way to go about it. Not how long does a CMOS take. arrange things in this manner, and then ask how long does single physical measurement take, and how long. You note these are Z-basis and X-basis measurements, so I have to be able to feed forward and apply a Hadamard gate just before the next measurement. So this also matters. How long can I take my measurement result and then decide in classical hardware to either put in or not put in a Hadamard gate. At the moment, we're going to assume 100 nanoseconds. It's can't be done at the moment, but it's a reasonably conservative number in the medium term. And it's the sum of these two numbers that sets the cascade that is quantum computation. Now, I'm not saying you would prepare your entire algorithm flat, all right? You can see it's a staircase. So a better way to think about it is you have a computer, and then the computation goes like a firecracker chain, right, through the computer. And you come back to the old part, which is finished with, when it's finished with. So it's a kind of glorified staircase, goes around and around, back and forth across the computer. And this is really what's going to be going on inside. Here's a little picture of, we've done all of our offline processing, and then one of the single layer logical measurements that determines where we teleport to. That's a small fragment of this piece. And look, you might say, come on, that can't be reasonable. Looks like you introduce compute overhead. But remember, the overhead is only this piece. 4C knots, a few preparations necessary. It's trivial compared to the fact that we're doing T-gates here, right? So it's completely negligible. It's a pure space-time trade-off. And already, with the data we've got, we can now say, well, how long is my algorithm going to take? We know how many controlled rotations we're going to do, because we're going to implement them one at a time, one after another. We know how many T-gates are required per controlled rotation. And we know that each one of those T-gates takes effectively the time of measurement plus the time of feed-forward processing to implement. So before we've even worked out how many qubits we need, we know that using this technology, superconducting quantum computer, we're going to require 14 days to calculate the ground state energy of Fe2S2, which is an acceptable number. We hope that it will get better in time, but it's a good ballpark. It's not 14 years, right?
Honestly,
yeah.
So you do the MZ and then you select one of those four things.
That's right.
And then that information is used with the next MZ to figure out what to do.
Yes, this next one depends
There's
on
some
lots
classical
of
logic.
measurements and this one.
Yeah, okay.
And then the next
Because
one,
the state got affected.
that's right.
That S, the way that the S works got affected that. So you have to keep feed forwarding the classical logic, but that's easy to do.
That's easy. The computation is very simple.
Yeah, that's.
I mean, in 90 nanoseconds plus 10 nanoseconds for rotation, not so easy, but believable.
Okay. That could be done.
It's a bunch of parity and very low complexity computations. So we know how long the algorithm is going to take, 14 days, 2 weeks. But we don't know how many qubits we need yet. And as I stressed at the beginning, the answer is certainly not 113. So we're going to use the surface code because, in my opinion, it beats everything hands down. You only need a 2D array of qubits, nearest neighbor interactions, and if we can get to 3 nines one day, which hopefully will happen in the next 2 years, then we can realistically imagine building one of these devices. So everything else requires long-range interactions with much, much lower error rates, and I'd be stunned if we ever manage to implement any code other than this one. So, physically it works so well because you're only checking 4 qubits locally, and you do that by initializing a qubit, interacting with its 4 neighbors and measuring it. A tiny number of gates, so very little needs to work to give you reliable information on where errors are. So this is a distance 3 surface code corresponding to this red line. So here you basically can see the logical error rate per round of stabilized measurement as a function of the physical gate error rate. And then for higher and higher code distances, so a distance 5 one is obviously a bigger square, and so on. You get more and more error suppression. And you can fit this entire graph below a certain point, so below about 10⁻⁵, this entire graph is fit extremely well by this formula. And one thing that's nice about this formula is it shows that effectively the code behaves as though the threshold error rate is 1 over this number, so 2%. Now that doesn't mean you can build 1% error qubits, but there's this non-linear region in its error behavior. And if you extrapolate the linear bit, then it behaves as though the threshold is 2%. The point being that if you are well below threshold, you are really, really well below the threshold. But around 0.2%, you're a factor of 10 below the threshold, and you have very rapid suppression of error. If you're around 10 to the minus 3, 10 to the minus 4, you get enormous suppression of error with increasing code distance. This is about a factor of 200. So, what we're going to do is we're going to use those square patches that we saw on the previous slide. So here's a square patch from the previous slide. We're going to use the error rate of those square patches to upper bound the error rate of an actual computation. So this is a conservative bound. If we actually do this computation for real, and I have a student working on doing this computation for real, we should get much better numbers. But what are we going to approximate it as? So, in a given volume, we could have, and I'm not going to go through the details, white is primal, the dark ones are dual, and it's just two different types of defects that connect the computation, period, no more detail. So let's imagine we have a forest of primal defects, then we can connect one to its neighbor, and we'll approximate the error rate of a chain from here to here by the error rate across this square. So this is a generous upper bound, because in actual fact, there's less boundary for errors to begin on and end on. Okay? Same, an error rate from here to here, approximate with one of these squares. An error around one of these, approximate with one of those squares. And that's a really generous upper bound, because there are very, very few error chains that meet up with themselves. That's actually quite a strong restriction. There aren't many of them. And then we have two different types of defect, primal and dual. So we double that again. So the doubling is for two types of defect. The 3 is for 3 classes of error. This is the duration of a plumbing piece. So you'll notice there's these little square bits and then prisms. You can build an arbitrary algorithm out of just these two types of block. And so that's what we do. We need to keep any two different surfaces separated by the code distance, which is d. So this prism here is length d. This cube here is edge length d on 4. And so the characteristic scale of this structure is 5d on 4 cubic. All right? When we increase our code distance, we double our code distance, the volume of our algorithm goes up by a factor of 8. Okay? So this is this 5d on 4. That's the duration. How many of these layers that we have, times the probability of logical error per round per plate. Okay? It comes out to this simple little formula. That's where it's from, and we're very confident that that's a very generous upper bound of a logical error rate that will get significantly better when we do the real analysis.
Are you including error chains that go up in time?
Yeah, so what happens is you might say, well, in this picture there are no error chains. There's no way an error chain can go up and down because there are no defects that go up and down. Everything's a forest going up. So surely there might be other cases where, for example, here, an error chain can connect from here to here. But if you actually go through the details, in this picture, for example, an error chain that starts here and ends here is topologically trivial. You can deform it to nothing. Okay? So when you start fiddling around with different geometries, you can show that this is the worst possible case. And that any time you actually add bends, you introduce more topologically trivial errors, and you reduce the error rate. So it's a detail, but thanks. That's a good question. All right. So more detail. So we have a way of calculating the logical error rate of one of these pieces. And we call them a plumbing piece, just because why not? It comes off plumbing. All right. Each one of these little regions, these 5d on 4 cube regions, we call them plumbing pieces. We need to know how many of those we have. Well, firstly, we know how many single logical qubit rotations we have. We know how many T-gates per rotation we have, so we know the total number of T-gates. This number, 10 trillion, give or take. We're going to assume a gate error rate of 10 minus 4. I know this is ambitious right now, but if we're going to build a computer that solves a problem like this, we're probably actually going to get there one day. 5 members, yeah. distillation. So when we inject, that's what these colored things are, a single physical qubit is a logical qubit. There you get a certain error rate, and then you can distill. So this is one round of distillation, a second round of distillation. Each time you do that, you suppress the error of state injection using this formula 35 So it rapidly goes down, and we only need 2 rounds of distillation to get to an error rate that is less than 1 on this number. That means about 500 quantum pieces per T-gate, about a quadrillion quantum pieces total. If we need to make sure we have no errors in all of those quantum pieces, we only need a distance 15 code, which is quite remarkable. It's just because the surface code works really, really well at 10⁻⁴. So if we assume the surface code cycle, the whole lot, all the initialization, the unitary gates and measurements takes 500 nanoseconds, then the time of one quantum piece from here to here, 5 beyond 4 rounds, is about 10 microseconds. And that means, since we know how long the total algorithm will run for, that we can fit about 1.3 to the 11 of these quantum pieces in time in the total algorithm execution time. What that means, since we know we need a whole lot of them, is that you need a factory of this size. It has to have a certain size to do all the distillation that needs to be done in the time that is available. So we then need to know how big just one of these pieces is. That's easy to do. Each unit of D is 2 qubits. So you end up with twice 5 beyond 4 squared. All right, qubits per piece. And you get 50 million qubits as your answer. 50 million. From an algorithm that on paper looks like 113 qubits, it becomes 50 million qubits. So, what's the summary? Arbitrary angle rotations are extremely, extremely expensive. Never, ever, ever lump an arbitrary angle rotation together with Clifford gates. Okay, they're at least 4 orders of magnitude more expensive. Even with a low error rate, 113 qubit algorithm becomes about 50 million qubits. There's no point telling the public that give me a few hundred qubits will outperform the best supercomputer. It's just not true. We're always going to have errors. As soon as you switch on error correction, the number of qubits will increase. There are obviously a lot of people working on bringing these numbers down. Of course. Coalescing, which is basically taking multiple control rotations and sandwiching them together, right? 2 individual rotations of some angle θ1, θ2 is much harder to implement than 1 rotation of angle θ1 plus θ2, right? Because it's still the same number of discrete gates to approximate the double rotation to the same accuracy, right? So it's a smart thing to do. People are hopeful that you can reduce the number of rotations by a factor of 10. Nesting, that's more parallelism. So the circuits I showed were very, very serial, this kind of zigzag V shape. People are hopeful that you can take separate V's and make them more parallel, so 10 times faster. There's something called the gearbox circuit. This is a good way of doing a small angle rotation. And we don't know exactly how much that will help in this particular case, particularly if you start coalescing, but it seems reasonable that a factor of 2 could be in there. There's some work by David on binary rotations, a different way of decomposing rotations. We're looking into that. Topological compression, making these things small. All right, tough problem, but there should be plenty of scope to make it smaller. The last 6 months, there's been a lot of improvement in the algorithm, so there's a lot of hope that we're getting better. And, you know, while it will get better, it's always going to be a big number. Okay, we're still going to be looking at millions. So in summary, you know, before you ever say we need a few hundred to a few thousand qubits, we're going to do something amazing, really, really think, is that true? It's probably not. It's highly unlikely to be true. Thanks for your attention.
Bits of the energy are you measuring here?
So this is a good question. So we debated for a long time to what precision you need. There's some debate as to whether you need really hard tree or micro hard tree precision. So this is a ballpark estimate for really hard tree or micro.
You have to know bits.
That it's the actual rotation.
No.
It's 10,000 total steps.
And in this picture, is there a way to show us the fraction of qubits that I'm looking for like a 10-to-1 ratio in distillation? Can I see from that picture that I'm mostly distilling?
Yeah, I mean, you can see from
Is that what the
first slide, right? The vast majority of the computer is preparing ancilla states to do arbitrary rotations. Like 99% of computers.
And those are the higher, the plumbing pieces that are higher with the colors on top?
So the small dense ones, that's first level distillation. This is the second level distillation. The output is here. This goes and then does TO.
Sorry, I missed the beginning. What balance do you have in formulas?
So this is something I talked about. The best I could get out of the people that wrote these papers was that approximately 10,000 total steps are required for sufficient accuracy.
Oh, I was wondering the formula.
I can't even tell you where that number came. At Hastings, after much debate and much thought, going through his papers and asking, well, does this formula gives me some error bands? Just gave you this one. So I think the most honest answer is that the field doesn't really know how many total steps to get a given accuracy, and even what accuracy is required for each problem. So I'm really trying to narrow down better than this, talking to people that should know, and I couldn't find anyone who could give me a good answer. But yeah, if you do have a better answer, tell me.
Following your statement about the 113 algorithm,
yeah,
and the 50 million
physical qubits.
I mean, formally with current technology and current dreams, it will be impossible, right?
Not impossible, but you're looking at 20 or 30 years. That's life. If we double every year, from now, it's 20 or 30 years away. Sorry.
John had a question.
Sure. John was laughing.
Are there any magic angles where you expect the distillation or something to be super efficient?
Yes, there are. There are actually a lot of different. So Hadamard and T are not the only ways of building these rotations. There are many, many other options, and we certainly look at that. For these algorithms, you really do need to be able to do arbitrary angle rotation. So it's a matter of choosing.
Oh, because you have different interactions.
That's right.
Okay, yeah.
But it's certainly true that there are other gates than T that you can distill. We are looking into that. Unfortunately, they frequently seem to be quite expensive to distill. But there's certainly work out there saying that if you use other gates, you might have shorter sequences. If you use multiple different gates, if you use Hadamard and T and V and A, all different types of magic states, mash them all together and build a sequence using all of them, right? You could get shorter sequences. But the devil's in the details. Usually these other states are expensive themselves.
But that's that 53 number, which
That's
when
right.
there's log of epsilon, so okay, you're looking at factors of 2.
Yeah, exactly. Yeah, yeah. Yeah.
In your algorithm, did you assume a perfectly prepared initial ground state, or did you actually?
No, yes. So again, the best I can do is talk to people, and most of them seem to think that that will be small overhead. Hopefully. So there's, for the people who didn't understand the question, so the algorithm I showed is phase estimation, but it assumes an adequately prepared approximation to the ground state. Okay, and there's a Hartree-Fock state that most people think is sufficiently easy to prepare and sufficiently good that you don't need to do something more complicated. And so you neglect it.
Okay. Any more questions?
I just wanted to make a comment. I see there is a missing effort in the case of quantum chemistry, in the same sense that in Laura's talk yesterday, we follow the approach of starting already with the complexity when the quantum platform allows, for example, for a continuum of sonic modes, you use them, you don't discretize and reduce to qubits, because then you get like in John Preskill's science paper where he reduces every mode, every qubit to qubits, and then of course you enter into the millions. Here is the same. You want to simulate quantum mechanically the complexity of a chemical compound, which of course when you reduce to qubits, you go to these millions, and you were really minimalistic in this thing, right? So I would say that the approach that is not being explored yet, in particular in quantum chemistry, is to try to simulate complexity with complexity. That you start with a complex chemical compound that is solvable quantum mechanically, and by minimal modifications using lasers, microwaves, or whatever, you turn the model into non-solvable.
And I agree, but for me what's missing from that field is an analysis of errors and a study of what can be done classically, particularly approximately classically. Because it's unknown if you can take unerror-corrected components and outperform an approximate classical algorithm. They're really good approximate.
I think this is the way, so let's say all the effort, the bottom-up approaches that we are doing are great. I think this is a good way of assessing the problem. But the real near future is simulating quantum mechanical complexity with quantum mechanical complexity and small variations. You see, so you start in the same way that we know models in condensed matter in quantum field theories. You say this is solvable, and then you add a term, and it is non-solvable. In the same way, you can start with a chemical compound that is very well known, an alkaline or whatever, and then you make small changes, and you know that this will be. But nobody knows what is solvable and what is not solvable.
That's right. And no one can say, if you go for this error rate of this set of components, it'll work. Right? Whereas with this approach, I can. And yes, the number's big, and yes, it's a long-term project to do it, but of course, we're working from both ends to try to bring these numbers down. The numbers are a lot better than they were 10 years ago. There used to be astronomical numbers, 10 to the 20, stupid numbers, right? They're at least reasonable numbers now. And yeah, you know, I would love to see a similar analysis in that area, which I think is very promising, deserves a lot of focused study, but honest focused study. Acknowledge that you have to beat an approximate classical algorithm, and you are definitely not going to be able to do that forever because errors will overwhelm you. Where is that line? We don't know. Very interesting question.
Right, so let's thank our speaker. Right, so the next speaker will be Vadim Smelyanskiy on the functional role of tunneling and quantum annealing with a D-wave machine.
I would like to thank the organizers and let me start. This is a collaboration with the team with Vadim from Davide and Mark Bittman from MSU and who partnered with Sergio. And this work is related to quantum annealing algorithms and physics implementation of that algorithms to some extent in open system environment with D-wave machines. Just to remind what quantum annealing is, just very briefly. So in quantum annealing, in usually called quantum adiabatic evolution algorithms, which are meant to be initially in a closed system environment, actually, an ideal quantum environment. You start with the Hamiltonian, which is your control Hamiltonian, and you evolve it slowly in time, preparing the system initially in the ground state of that Hamiltonian, and then evolving it in time in such a shape that at the very end of quantum evolution, that Hamiltonian encodes the optimization, classical optimization problems you want to solve. And then, since you arrive in a ground state of that problem, by measurement you recover. So usually this could be wrote in this way, and this is a simple linear interpolation between the initial Hamiltonian Fault driver, whose ground state is easy to prepare, and the final Hamiltonian Fault problem, whose ground state encodes the solution of the optimization problem. And then you follow the adiabatic theorem, and then you evolve in a ground state. Now, the real complexity of that algorithm is determined by how slow you evolve. And that slowness, at least in the ideal system case with no coupling to environment, is determined by the minimum gap. Because the spectrum of the problem becomes quintessentially quantum, right, as we evolve. And there will be a small gap somewhere, the minimum gap point, and how that minimum gap scales with the system size ultimately determines the complexity of the problem, because the runtime that you need to do, at least in a uniform evolution, is inversely proportional to the square of the gap.
I just wanted to put myself in objection forward about the rigor of that formula.
I think, as far as I'm concerned, there is a lot of complexity that I can also argue about that. What I'm saying is right now, let's figure that formula. It's good enough. For me, it's good enough. If you want to argue, I can argue back, and we can argue indefinitely. In the spin glass systems, with the complex density of states, with the delicate behavior of the spectrum at the matrix element, all that, that's not talk about. So, but the bottom line is really this. Whatever that minimum gap is, right, there is a physical process that limits the size of the gap. There is a fundamental physical process. It's not the only physical process that limits the size of the gap, but this is the most obvious physical process. So, and you could view it in the following way. If you have a multi-well potential, which is usually represents a spin glass system with a spurious local minima and all that, right? So what you really want to be, you want to end up here. But you're not there. You start your algorithm saying it's a simulated, even if you start with simulated annealing, you start somewhere with a higher energies, right? And you want to converge down. But if you do quantum annealing, you start with a very large transverse field, so you are again starting somewhere higher energies, except now when you go down, you're really evolving your potential shape and you're associating the time. So the minimum gap is the point where one potential well of your initial state and another potential well of your final state become equal with energies. Then in the ideal system, in the absence of environment, the process that is available for you in quantum annealing is this tunnel. And then you have to wait long enough until you establish your tunneling process, because you have a tunneling splitting between symmetrical and anti-symmetrical state. And as your system evolves, you have to be able to tunnel, and the levels move forward. You have no way of tunneling back. That is a process which is determined by Landau's inner effect, and then you're there. So ultimately, whatever we discuss, the square of the gap or not the square of the gap, the physical process in place is that you have to move coherently with sufficiently, you have to allow yourself sufficiently slow evolution to have a time to tunnel. That's the physics. And therefore, it makes sense to investigate more accurately that tunneling process when you have a machine as a D-wave machine that we have a lot of mass and a lot of noise and a lot of calibration errors. But maybe we can sort out that tunneling effect and then shed a light on the machine performance, or at least the perspective of that. Maybe the D-wave machine already have it. And that's something to look at. And as a positive token, not necessarily will be talked a lot in this talk, but for future, if you have a tunneling, then there are two fundamental different scalings that happens versus quantum mechanical tunneling versus simulated tunneling. In quantum mechanical tunneling, really the tunneling amplitude is exponential in length of the tunneling barrier, but it's only a square rooting exponent of the height of the tunneling barrier. Well, and then you have to divide by some h bar, which in this case is not an h bar, some effective parameter related to transverse field, which does the spin field. Now, when you do thermal annealing, which is simulated annealing for any classical process, that go over the barrier, well, then you are really proportional to the in exponent to activation energy, which is the Boltzmann distribution. You can go over the barrier. So this is the linear power in exponent versus the square root. So maybe you can trade a little bit of this length of the barrier versus the height. So if the height is very large and the barrier thickness is not as large, your tunneling is winning over activation. And there was a lot of questions about the quantumness of Davide machine, right? So what we like to make sure that when we actually design a problem, but the Davide machine is solving the problem by doing the tunneling, or maybe we think it's doing the tunneling, right? We need to convince ourselves that the problem solution is in fact by means of tunneling, rather than by means of terminal effects. That's something, we are not making any statement whatsoever, by the way. That is not obvious to me at all. That even if you are making your solution by means of tunneling, even if you manage to completely isolate yourself from the environment, you have any advantage whatsoever compared to classical algorithms. But still, let's see if this is actually, a tunnel. So I want to move very quickly. This is a Davide machine device. This is another speed, but I'm not really an expert in superconducting circuitry. For me, what is important here is that you have a double well potential in our speed, the flux going one direction, flux going another direction. You have probability of tunneling between these two states in a single qubit device, and then you vary the height of the potential well, and then the height of the potential barrier. I'm sorry. And this way you vary your tunneling. At the beginning, your barrier is not as far, your tunneling splitting is large, and your zeros and ones are essentially qubits at the right and qubits at the state on the right, qubits at the left. Flux up and flux down. And then you create essentially in a two-state representation, you have your bias fields, which are biasing your qubit, right? That's a sigma z Pauli matrix, if I assume plus or minus to the left and right. And then there is a sigma x, which is really a tunneling barrier, right? That allows you to split between left and right. So that's your tunnel, that's what we call transfer speed. And then if you have many qubits with each other by magnetic coupling between them, by overlapping fluxes with each other in a good way of saying, there is a really eigencoupling between the qubits. That's all I need to know. And what I'm going to do, we are going to change those coefficients so that at the beginning system favors symmetrical states in each qubit. Symmetrical states meaning equal superposition of right and left, which is in the power matrix corresponds to spins, effective spins, looking in the x direction of the field, right? And at the beginning. And then at the end, they're going to be basically representing a solution of a classical Isaac problem encoded by these coefficients, which is what we need, right? So that's a thing. Now, Davide has this architecture, which they call chimera architecture, and when the qubits are, both are the couplings between the qubits shown by edges and the qubits shown by dots, they're organized in these 8 qubit structures, and basically each qubit over here is connected to each qubit on the other side, so 4 connections, but there is no qubits connected inside of this line. That's called a unit cell, they call it a cluster. And then you can couple clusters with each other by drawing this line, so each of the columns on the right coupled to its own column on the right, another column on the right, another column on the right. And then the left of this column is coupled to the vertical one. So it's a bipartite structure. This coupled to this, and this coupled to this. Okay. And there is a reason to that. It's a natural layout that corresponds to that. So what we like to do, we like to select a few of those unit cells and design a problem that involves a solution of some optimization problem that we know by construction must involve some bistability and tunneling in order to solve. So the tunneling will then play a functional role, because if there would be no tunneling, the problem will be solved, as we will show, in a very slow fashion and would not be able to solve efficiently. So what the idea is to try to model the system and try to see how that solution corresponds to the modeling with the noise and all that. So in fact, the wave has done, in reality, there is almost nothing new, because the wave has done this analysis before, except they have not really done an analysis. they did design a system with 16 qubits for clusters, and they made sure that the minimum gap is extraordinarily small. It's in a microkelvin regime. And once they got this gap, they found that the typical time they need to slow the rate of their quantum annealing is in fact corresponds to some fairly good precision to Landau's inner formula. So the rate of the annealing is linearly proportional to the annealing rate and inverse proportional to the square of the gap. That's a two-level system, Landau's inner framework, with no noise. So that was an observation. That the quantum annealing time versus the success rate is related by the simple Landau's inner formula with a closed system with no noise. And this was not really a new thing. It was actually known pretty much way back, all the way after the Leggett and Kavortyr's paper. There was a paper by Rama and others that actually show why that happens. And this goes back to the simple argument. So once you move past the avoided crossing, if your avoided crossing is very small, then what happens, you reach the point where your rate with which you move is becoming faster than the rate between an environment can make a transitions between the states. That's a freezing point. And at that freezing point, you can actually assume that what limits your success is how fast the system makes the transitions between the states. And at that point, the tunneling mixing is already small. And so that really is determined by this formula, which is a second order perturbation theory really is in a tunneling matrix element. And what could possibly be also shown, that in fact, if the tunneling matrix element is much smaller than the dephasing rate, then this formula is correct essentially everywhere. All the way through the avoided crossing, that formula will be correct. Because your tunneling matrix element is much smaller than the typical width of the level. It's really a perturbation picture. And, well, this is the spectral density of the noise. But what is important here? This is your bias between the qubits. What is important? That if your bias is changing uniformly in time, it's a two-level system, and your bias is changing uniformly with time, then the derivative is constant. What you really need to do, you need to take a probability of transition from one well to another per unit time, and integrate that over time. That will give you the dimensionless quantity, which when that quantity is of the order of 1 or more, then obviously, in this case, you are already saturated, and this is what you need to be looking for. That gives you a scale of how fast you need to move. Well, when you integrate over this epsilon, obviously, this is uniform rate of change, then integral over time could be replaced by integral over epsilon. So you could see over here, when you integrate over epsilon, that's a delta function in time. Once it's a delta function of time, this is spectral noise density, this goes to 0. So the whole thing is proportional to Gn squared. And that's where it is. So essentially, this is macroscopic resonance tunneling is like a nonlinear filter, essentially. Well, you have a line shape, it's like an absorption, right? You have a different probabilities, amplitudes of absorption at different frequencies, but the integral probability of absorption is only really determined by the oscillator strengths, and that's what really is shown here. So that was an observation that noise is basically redistributing probabilities over different frequencies, but once you integrate over all of them, the result is essentially noise independent. It's a simplification, but that's what really is. So anyway, I'm not going to go in details, but they did analysis with the 8-qubit tunneling, and they did found that in the limit of very low temperature, if you extrapolate, if you believe the extrapolation procedure and all that, then you do uncover that law. There was no real modeling. It was just an extrapolation procedure to show. Well, what we like to do, we like to start gradually understand what is going on in those problems. So what are roles of noise and whether this formula always holds. Because one of the upshot of that formula, that the positive news, it looks like the closed system Landau's inner effect. The negative news is entirely a consequence of incoherent tunneling effect. And the key word is that the tunneling splitting is much smaller is much smaller than the dephasing width. Now, in that regime, system has no memory. That means that, for example, if you do want to do local quantum adiabatic evolution, for example, adjusting the rate of your evolution instantaneously to the value of the gap, in which case you wouldn't get inverse square of the gap. You would get a linear of the gap. You wouldn't be able to achieve that result because the system has no memory. So you would be stuck with the inverse square of the gap no matter what you do. So it's not really a coherent effect at all. And we have a reason to believe that that effect would be simulated even on a large scale by fast integral Monte Carlo, and that's it. So, but that's why we want to look a little bit more and see what is going on. So we designed a system with two clusters. Okay, we call them unit cells. Those are two clusters. And to simplify the analysis, what we did, we actually tried to do the system where all the couplings are the same. And how much time I left? Because this watch are a little bit confusing.
You have about,
Huh?
about 10 minutes.
10 minutes, okay. So when all the couplings are the same, then this system of two clusters would be in fact represented in a form of a larger spins, like a molecular magnets. That is an analogy that actually works here pretty well. So you can introduce, remember these unit cells are columns of 4 spins in a column. So you can introduce a spin of a column, a superspin, which has a maximum value 2. It's a 4 spins 1 half. And then the total Hamiltonian could be the total Hamiltonian of a unit cell can be represented as essentially a coupling between the spins within the unit cell, between the two columns. That's a column 1, column 2, and also a bias. If you assume that your bias are the same within each column, then this will not break the symmetry of permutation of individual spins. It also could be represented as in terms of a column. Now, the only thing that does not fall into that symmetry class is essentially coupling between the clusters, because you only have one coupling between this spin and the other column. However, the point is, because this has 4 couplings, and this has 1 coupling, so when I break the symmetry of the column, the permutation symmetry, when I break one spin, I violate way more constraints here than here. So numerically, you can convince yourself that even when you make all couplings the same, the factor is 1/4, that is a sufficiently small number, and results are pretty accurate if you live in this large spin space. Well, you can also convince yourself that the low-lying energy spectrum of that 2-cluster system, and as a matter of fact of a 4-cluster system is even more, is actually determined by the fully symmetrical subspace with the largest maximum value of the spin. So now you can create the analysis based on this molecular magnet ideology and large spins, and people study tunneling in that context. So the idea to approach tunneling is to each column, each superspin, right? We introduce its coordinate, which is a projection on the z-axis. That will be my coordinate q. And then the momentum of that will be corresponds to the projection of the x-axis with the square root that reflects the vector scale model. But there is a momentum, which is a quantum operator. So you can do it for all 4 columns, right, in this case. And what you can do now, is to study this effective Hamiltonian with the coordinates and with the momentums. And the ground state of that Hamiltonian resides at the point Q that minimizes this effective potential. When I set momentum equal to 0, that becomes an effective potential. So I can follow that local minimum, or initially it's a global minimum. If it's become a local minimum, then I have a tunnel. So, and we do this analysis. And the basic idea of construction that creates that local minimum is this. For 2 clusters, one thing we need to know that very early on, when the Z magnetization is very small, X magnetization is large, Z magnetization is small, you really, the coupling between the clusters is 2nd order in magnetization. But the coupling to the bias field along Z-axis are 1st order in magnetization. That means that we now know how to treat the system. If we apply to 2 clusters with a ferromagnetic coupling between them, if we apply local fields in the opposite direction, then the system initially would move, this cluster would move out, this cluster would move down. However, later on, we can adjust this ferromagnetic coupling to be strong enough so that in fact at the end, the global minimum corresponds to clusters in the same direction. And at the beginning, system would not know about this, but at the end, it would know about that. And of course, the local minimum would correspond to them in opposite direction. The global would correspond to them in the same direction and the direction of the largest field. So that's second order coupling in a small parameter at the beginning, and the magnetizations are first order. So local fields dominate at the beginning, they're losing at the end. So that's the thing, and you can do numerical simulations and bifurcation diagram study in this, two cluster thing to convince yourself that you are, for certain values of the field, you are locking yourself in a local minimum. Blue and black clusters are looking in the opposite direction, not in the same direction. And there is a ratio of intercluster energy which is very small at the beginning. However, the total ground state are when blue and red clusters are looking in the same direction. So we clearly created a bistability here. And you can analyze it through the phase diagram and all that, but this is absolutely the key figure. So this is an energy of the local minima of that multi-spin system. And it counted off, in fact, the minima that you start at the beginning, when all spins are along x direction. So that minima is a global minima. It's like a parabolical shape that evolves up until that point. And then there is a new minima occurs early on. It's about 0.2 in an annealing parameter, where there is a saddle point and there is a new minima that becomes global over here. And that new minima, the red one, does correspond to full ferromagnetic state in both clusters in the one direction. That means that over here you have a global bifurcation. And in fact, if you do careful analysis by simulated annealing, by spin vector Monte Carlo, when you use all these rotators to be a classical rotators and a combination of transverse field and isocouplings, what are you going to get? You're going to get basically scaling of the Kramer's escape rate that you need to rotate your cluster in the right direction, overwhelming the potential barrier, which is shown over here. And this is a comparison of the Kramer's escape rate numerically with analytical prediction of the barrier height that we can do in a large scale picture. They're very exact, very accurate. So you are really having classically a large spin that has to hump over this barrier, which is fairly high. And the barrier, of course, is very high because you're breaking a lot of bonds. So, yeah, so that's pretty much the picture. And one thing I wanted to tell you what happens in a closed system. In a closed system, you have a tunneling right there. In an open system, you do not. First of all, the setting of our experiment and analysis was such that this gap was fairly large, actually. It was larger than all the decay transition rates in that system that you can carefully compute, which I'll show later. Therefore, by the time of evolution, the annealing rate was slow, less limited by the wave electronics. So really, you were thermalizing fully here, even though you were in a coherent tunnel regime. But here, you have essentially a boson-assisted tunnel, because you are still here, and you thermalize, you have here, but as you move here, you essentially emit bosons and go from this level to this level. That's how what is the limiting case of your performance. Well, you can calculate this using some noise models, and I'm not going to go into details, but there is a pretty good case for a combination of a low frequency noise and a higher frequency noise, which has an ohmic shape, and the divided analysis. I don't believe this is really the proper model of the noise, but it is good enough to describe the MRT line shape and on a single qubit level, and you can convince yourself by doing some analysis with the NIBA technique and all that in this freezing point, once you pass through, this is again the probability of transition, except it has one modification. Any parameter that you have, like a reconfiguration energy, the line shape, and there is a parameter A, which is the sum over 1/4 over the relative magnetizations, over all qubits. So that parameter is here. But for two clusters and a large gap, that parameter is not dramatically large. In fact, that parameter is very small at the avoided crossing because of the symmetry. And it becomes to grow close to the freezing point. So if you do all that analysis, then you can do numerical, that's the end result. So you can do numerical simulations based on this simple theory, really almost analytical. I I did all that on Mathematica, for example, so it's there. And we compared with the D-wave and with the spin vector Monte Carlo, and we didn't really, at the moment, use fitting parameters, because we just use single qubit data for that. And you could see that this is the result, which is for this modeling with generalization of NIBA technique, which is a non-interacting Green characterization. This is D-wave data, and this is spin vector Monte Carlo and path integral Monte Carlo. And this is the probability of success as a matter of ratio of this field that actually can cluster. And you could see that there is a reasonable agreement between the D-wave and theory, and D-wave performs definitely much better than both spin vector Monte Carlo and path integral Monte Carlo, and we can explain why. Because the other two do need to go over the classical barrier, and D-wave does not. So that's whatever short message which I wanted to tell, that looking a little bit deeper into what tunneling does in the system, you may discover that in fact the performance is quantum.
Can you say something about the KT limitation on annealing as a function of number of qubits?
Well, yeah, even in this example with two clusters, it is already smaller than the temperature. Because the gap here is 0.112 GeV, and the temperature is about what? It's a little bit bigger than that. It's a 0.8 Kelvin. So that you mean KT limitation in terms of temperature?
Yeah.
Even here, the gap is already smaller than the temperature. However, you really have time to thermalize. And what you would need to do here to beat that limitation is to move fast. Because you have a big separation, huge separation between the very large gap and actual Landau-Zener rate is not very large at all. So you have ability to go faster and faster and faster and still neglect Landau-Zener transitions. And then once you move significantly faster than the decoherence time, which is possible here, then you will be in a coherent regime that you can actually demonstrate. So the size of KT is not of significance here for this type.
When you try to compare the D-wave data to the various models, to me it doesn't look like you know the parameters of the D-wave machine well enough. I would have to look into it carefully, but you know, it's a very complex analysis of how to get the thing. So how can you know that you're plugging in the right materials to be right parameters?
So this is what we do, and let me just say what we do, and no more implications. We take a single qubit MRT data from the wave, which is you can reasonably describe this as a sum of the low frequency noise and a high frequency noise. Low frequency, we take a Gaussian noise, it's a two-moment expansion.
Yeah.
Right, and then one additional data point for us, that there is a thermodynamic relation for a reconfiguration energy for that experiment. That means that the high frequency cutoff of a low frequency noise is smaller, significantly smaller than, say, a few megahertz. So that's a data point that we have. Then there is a data analysis that is hybrid model with some of these two noises, with high frequency noise being ohmic. And there is a data analysis that relates the MRT signal to the blue, which is experimental data. I'm not a guy, right? I have limitations in everything we see. This is all we can do at this moment. We have a model that describes the data in a single qubit model.
Yeah, but I'm worried about there must be other parameters having to do with qubit energies and various other things that probably the next, for example, I understand that has a pretty good fit to the data there. The next slide, you compare the next one. Sorry, a couple more. Yeah, that one. This one. I mean, you plug in these various models, and you make a conclusion that.
Well, let me tell you exactly what I'm doing here. We take a single qubit model, and since we know how noise dissipated, we use that model for a single qubit. Then since I have a large spin models, I can use each small spin is coupled to its own mass, I can derive equations of motion for the density matrix, play around with them, convince myself that's correct, at least theoretically. Then I'm saying, look, but there is nothing more than single qubit dissipation. If I know a single qubit, I'm not saying I do, but if I use a single qubit dissipation model that is there, and if I calibrate carefully the coupling between qubits, so at least I know them within 5% precision, all I can do, I can construct my many qubit dissipation, right, based on the single qubit model and play around with sensitivities.
Yeah, I'm just saying that there's a whole chain of assumptions here. Like when you calibrate and you get numbers, I need to know when you're calibrating and you're getting your numbers, what is the model dependencies on all of that?
Exactly.
So when I look at that plot and you made some conclusion
Exactly.
about this model works better than this model, to me, it's like, I don't know if that's really correct. Because you have a lot of assumptions going into evaluating your parameters based on experiments where you're assuming something is working in a certain way. How do I know you're extracting all your parameters in a way that is like, makes sense? There's a huge number of assumptions going in.
So the only other assumption besides the single qubit model, the data you show that's pretty good fit, the only other assumptions we have are calibration. Whether we have a calibration error, whether we do know the coupling Hamiltonian between qubits accurately. So we played around with that. We did accommodate second order susceptibility effects. And we also played around with the sensitivity study, what it means that we play around with the couplings and we see how sensitive it is. And within 5% error, it's not very sensitive. So what I like to say, I agree with you on everything, but I'm a theorist, I'm not experimentalist. All I can do, but I have to do a fair job. So all I can do, I say this is a single qubit decoherence, MRT, that are fitted well with the assumption that I have a low frequency noise with a high frequency cutoff, which is way smaller than the gap, and I have a high frequency noise with a high frequency cutoff way greater than the gap and linear. If I do that, then I extract two coefficients here, three coefficients. Line width, Stokes shift, which is a reconfiguration energy, and ohmic coupling. The second thing, I check that the reconfiguration energy and W line width are connected by thermodynamical relation through KT. That gives me so there is a certain things logic. Yes, I completely agree with you. If I look at the real noise model here, it could be a diffusion of the spins. It could have nothing to do with, when I say low frequency noise is Gaussian, that means I'm shoving things under the carpet. Of course, but there is only that much I can do with the data available. That's all. I agree.
I'm trying to get, it's, to me, we're making some, conclusions about what's going on based on a lot of assumptions. I don't understand.
Let me tell you one single data which I believe why we made that conclusion.
Okay.
If I assume that the barrier I shown you it's not tunneling, it's over the barrier escape, then I got the numbers that are way beyond any experimental uncertainty. It is completely clear that you have tunneling. It just doesn't make sense. So that's the real statement.
Okay, let's not speaker. Next speaker is Davide Venturelli on quantum optimization of fully connected spin glasses.
Oh yeah. Yeah, let's not go. Yeah.
Just go to 800. Yeah. 800 by 600.
Yeah.
You apply. You need to hit apply.
You need to hit apply before you hit OK.
Yeah.
Okay. Do that again.
Your work really kind of gets to.
You can't see someone now.
Yeah. Try hit apply though. Other people did it.
Let's apply the different one first. Then I will apply the correct one. You guys suggest this is the right thing?
I think so.
I will apply 2 weeks.
All right.
Okay. Let's brainstorm again. Yeah. Okay. Yeah. Big changes. Let's see. Yes. Okay. I can start. So I'm Davide Venturelli, I work in the Quantum Artificial Intelligence Laboratory at Ames, which is led by Vadim, who just gave a talk. It's another discussion, the one in the next 25 minutes on some D-Wave related results, but this time we're going to discuss on how to use the D-Wave to simulate, in a way, a physical system of interest, which is a fundamental quantum statistical model, the Sherrington-Kirkpatrick model. In other words, the fully connected spin glass. We're going to discuss some perks and details of the programming of this model in the machine, and we're going to discuss the effect of noise, calibration noise in a way, and to try to draw some preliminary conclusions of whether the machine can actually represent, or if you want to use the word simulate, a given quantum system that is fully connected to the glass. Knowing that we do not have the liberty to do whatever we want, we do annealing again. So every conclusion we do, we have, is an indirect conclusion of the annealing procedure. Small introduction about what is the protagonist of this talk is the Sherrington-Kirkpatrick model, which is defined by Hamiltonian, where every single spin, in a classical sense, the variable +1 - 1, is fully talking with every other spin in the graph. So for the sake of understanding of the model we are going to discuss, we do consider a random distribution of the coupling J alpha beta, which is taken bimodal distribution between +1 and -1. And I'm not going to renormalize these couplings as with the square root of n for the practitioners of thin glass theory that know that usually people likes to have an energy density which is constant. But in our case, we're going to make tests in the machine by keeping the couplings +1 - 1, meaning that the energy per spin will actually increase with the system size. But we're going to discuss the consequences of that. Sherrington-Kirkpatrick model is very interesting for physicists because it has an interesting phase diagram, for example. Even in the quantum regime, where you do consider the variables SZ as actually Pauli operators, and you add to the Hamiltonian the transverse field, you do have a phase diagram where you can distinguish a paramagnetic phase and the spin glass phase, and the phase separation occurs at well-known critical temperatures and well-known, reasonably well-known transverse fields, which, as I just mentioned, they need to be renormalized as a square root of n in order to understand the phase diagram. And when I say a spin glass phase, for the sake of this talk, I just need to remind you that whenever you are in a spin glass phase, you expect to be in an energy landscape where relaxation is very slow and the system is known to be hard. So if you are aware of the hard to optimize, meaning find the ground state. If you're aware of the current debate on whether the benchmarking of the D-Wave machines have been done on difficult or easy problems, well, we are definitely sure that if we were able to encode in the D-Wave machine the Sherrington-Kirkpatrick model, we are dealing with a difficult problem to optimize. And well, historically, I also think I'm aware that the Sherrington-Kirkpatrick was probably the first context in the physics literature where people started to hand-wavingly think of the role of tunneling when it comes to potential helping the crossing of the barrier. So it's also, if you want, an historical interesting point for the community of quantum annealing. But at NASA, we care about applications as well. We're not just, brainstorming on knowledge for the sake of advancing our understanding, but it's also, we care about applications. And Sherrington-Kirkpatrick model is, besides being an NP-complete problem, it's also very related to applications that we directly mapped efficiently graph partitioning problem in a seminal paper. And for us, it's also a reference point for embedding. Now, I believe Alejandro reminded yesterday what embedding is in annealing machines, meaning that I will do that too, but it's a procedure of representing a graph in a given hardware graph by using contractions of edges. And I just want to mention that if you have a problem graph that you want to program on the machine, and you have an hardware graph which defines the actual physical couplings between the qubits that you have on the machine, you well, you can always preliminarily embed your problem in a fully connected graph, which is a trivial embedding because a fully connected graph embeds whatever. And then if you have some results on the embedding of fully connected graph, you have a limit of understanding of what could be a potential performance of the overhead of embedding. So since we like limits, is also a reference point for embedding. And finally, my motivation is also generated by practical application problems, and I want to advertise it today. It's going to appear on the archive of a paper on planning and scheduling encoded on D-Wave machines. So in many optimization problems where you have to minimize some objective function, which is, for example, linear, but has some constraints, you very easily generate fully connected cliques of interacting bits or spins, if you want. So it's particularly common to observe whenever you encode, from a practical standpoint, a quadratic unconstrained binary optimization problem on an annealing processor. It's very typical that you have some constraints that generate effectively fully connected subgraphs, which can look random to So if you learn how to solve these kind of problems, you also have, and how to optimize the solvability of this problem, you also have a tool to solve interesting problems. Okay, so let me remind you what embedding is. You have a problem, an optimization problem, and you want, this problem is defined on a graph. In our case today, this is going to be a fully connected graph. So everybody is connected with it. But reality is that this graph is not going to be the graph you have on the machine. So Vadim reminded that the graph of the machine is a bipartite graph where you have clusters of fully bipartite unit cells. Now, how can you make sure that the bits that are connected in the logical graph you want to implement get connected in the physical graph? Well, one procedure would be to actually pretend that a subset, a connected subset of the hardware graphs behave like a single qubit. And if you can do that, you contract them to a single qubit, you can exploit all the edges that spark out of this connected component and maybe represent your graph. So this procedure, which is minor embedding procedure, it's a topological procedure which, if you want to do it optimally, it's a NPR problem by itself. Now, but it's what we need to do, and what you end up at the end is with a problem where every qubit, which represents your logical qubit, is actually a cluster of connected qubits, which communicate to some other logical qubits through one or more edges of the physical graph. So whenever you want to couple 3 logical qubits, what you really should have in mind is that every logical qubit is actually a chain or a cluster of physical qubits, which has some connection to another cluster of physical qubits. And how can you enforce the fact that they behave like one? By basically ferromagnetically coupling them sufficiently strong. This is like naive thinking, where you penalize from a classical standpoint the fact that they break the ferromagnetic bonds. But this procedure carries with itself many choices. Like you can ask yourself, okay, well, if this qubit needs to behave like a physical bit, like a logical bit, what is the correct ferromagnetic coupling I should put? Like, if you put too much, then it's super stiff. It will never tunnel. It will never flip. While if you put too less, it's going to break the chain very easily. And I want to point out that this embedding procedure changes the energy landscape of your problem. Now, if you have a very nice pictorial view of your logical problem energy landscape, now when you encode every bit in a subset, in a set of physical bits, now your logical solution are separated in Hamming distance by all the states which represents the breaking of the ferromagnetic bonds. So this means that from an energy landscape point of view, you are introducing barriers when you create embedding in the problem. Okay? So you obviously change the dynamics of annealing. We don't know how, but meaning that the problem can be easier or more difficult. Okay, so let's target the Shelton-Kirkpatrick model. Let's take a fully connected graph and say, I have the D-wave machine, I have an annealer. Let's put the fully connected graph in the machine. And let's start a very simple embedding, okay? So this embedding procedure is systematic. You have a unit cell, right? Unit cell is 8 qubits. They are bipartitely connected. Now, if you want to create a fully connected graph out of a unit cell, what do? You take the first 2 and you ferromagnetically couple them. Now they are 1 qubit because they behave like 1. The second 2, you do the same. The third 2, you do the same. The fourth 2, you do the same. Now you have a fully connected graph. Okay, that was easy. We have a 4 fully connected graph out of a unit cell. And now you want to go to 8. How do you do that? Well, you take another unit cell, like this one, and you do the same thing. Now you have 2 4 fully connected graphs. And then you use a unit cell in between the 2. You remember Vadim explained to you that they're connected vertically and horizontally. And you use this unit cell to make sure that these 4 qubits fully connected and these 4 qubits fully connected, now they talk to each other. And effectively speaking, you created a graph where everybody talks to everybody. But in group of 4, these 4, they have 2 options to talk to each other because there are 2 edges, while they have only 1 option to talk to the other color group. And you can go on with this iterative procedure and keep on adding 4 more qubits by enlarging the triangle, which I just described. Okay? So from a scaling perspective, you do need 4n times n plus 1 hardware qubits to encode 4 times n qubits. So it's a quadratic overhead. You already see that whenever you want to encode a problem such as this one, you immediately have to think that even if you have 1,000 qubits, you can't actually have, you have the square root of 1,000 logical qubits. Okay? So that's one of the biggest bottlenecks of, for example, working with the D-wave Canary graph. Because interesting problem tends to be close, I mean, not close to fully connected, but highly connected anyway. So this quadratic scaling comes into play very often. But as I told you, this procedure changes the Hamiltonian. And I want to give you a sense of this. This is the Hamiltonian of the, pen and paper annealing. No, you have the Shelton-Kirkpatrick model. You have transverse field in the x direction. But what you really have on the machine is a quadratically higher number of qubits, some of which they just are ferromagnetically coupled, okay, and some of while the edges, so they're either the couplings are either the ferromagnetic coupling that defines the embedding, or the +1 -1 couplings, which defines the logical problem. And I want to point out the machine can allow us to set the energies of the couplings. But there's a maximum, which is 3.2 gigahertz. Okay? And what we're going to do is to say the ferromagnetic couplings are the higher energy scale of the system. Okay? So we put the ferromagnetic couplings at 3.2 gigahertz. And we, instead of increasing the ferromagnetic coupling to see the effect of the embedding parameter setting, we are going to scale down the logical qubits, the logical couplings, to a point where we have a ratio which is predefined. Okay? So this is going to be important because whenever I say I increase the ferromagnetic coupling to make the embedding more, tough, what I really do is I decrease the energy of the logical couplings and I keep fixed the ferromagnetic couplings. Okay. And since the temperature stays the same and everything stays the same, this has consequences about the noise. Okay. Just a pictorial view of the processor. We have here in NASA's 509 qubits. You know that there are there are 3 broken qubits. And if you want to encode a fully connected graph with the procedure which I just described, you can use the upper triangle and get up to basically 32, because we could go, but two qubits are broken, so you go to 30 if you want to preserve the symmetry of the embedding. So what I mean by this is that we are going to test the performance of the machine on the fully connected graphs up to n equals 30. Okay, that's what we can do. Okay, so let's have a look at this. Let's have a look at this procedure. How much time? Sorry, I'm not keeping. Okay, so I'm halfway. Very good. So what are we doing is now showing the performance of the machine when it comes to annealing. So how probable is that an annealing procedure finds the ground state of these problems? Okay, and I want to make a disclaimer at the beginning. We cannot decrease the single annealing sweep as much as we want. We have a bottleneck of 20 microseconds per annealing time, and we know that we would be better off in going faster, but we can't technologically. So this can, as shown by Matthias Troy in a recent paper in Science, this can result in an artificial speed up, like from the scaling point of view, but that's the best we can do for now. And another thing I want to say is, so there are errors, there's noise, decoherence, there's dissipation, and at the end of the annealing time, you will encounter sometimes some ferromagnetic clusters which should behave like one, that they don't behave like one. So, like what you see at the end is that this logical qubit, which would be representative of a single bit, so this logical bit, which is made of a chain, sometimes it violates the ferromagnetic boundary that I defined. And this violation comes with a price. It's an energy with the domain wall, but can be corrected, meaning that we know for sure that if there is a violation of my embedding, I'm not solving the problem, right? I'm falling outside the code space in a way, right? So we can correct this, and we can actually do majority voting, for example, or we can just randomize, and whenever there's a qubit, there's a bit which doesn't respect the bonds, define whether it's +1 -1. And this gives you an improvement over the probability, meaning that some solution that would be rejected because they fall outside the code space, now they are accepted. And this is why in this graph, which shows you the actual probability of finding the ground state, I have two bands. One is without error correction, and one is with error correction. So if you consider this error correction, you should just look at the upper color. So what you see here is that if you have n equal 4, so just a single unit cell, a ferromagnetic coupling of basically 1.5 is sufficient to give you the maximum probability of finding the ground state. Good. Now, if you n equal 8, you need to increase this ferromagnetic coupling a little bit to get the maximum. If you n equal 12, you have to increase even more. And 16 increase even more. And 20 even more. And 24 even more. And 30 even more. So the larger the system, the more connected the system, the larger the ferromagnetic bonds defined in Vadim needs to be. Why is that? Well, the reason for this, in our opinion, is that we are dealing with a problem where there are two phase transitions going on here. So there is one, which is a ferromagnetic phase transition of the chain. Remember, every qubit, every logical bit of the Smelyanskiy model is encoded in a chain of n divided by 4 plus 1 bit. So one thing is that this chain, at some point, will feel the ferromagnetic transition during the annealing, for which the chain wants to go from a paramagnetic phase to a ferromagnetic phase. Okay? And this thing happens roughly when the transverse field is equal to the ferromagnetic coupling of the chain. But there is also spin glass phase transition, as I showed in slide number 2, which means that there is a transverse field at which the problems start to become hard. The barriers raises up to a point where the relaxation time diverges exponentially. So, and this transverse field is actually proportional to square root of n, and it is inversely proportional to the ferromagnetic coupling which included the system, because, as I told you, the logical couplings are scaled down by a factor of 1 over the n. So what I mean is, during the annealing procedure, there's a point where the logical bits become stiff because they start to become ferromagnetic correlated, and now they can't tunnel easily from a all up state to an all down state, you know? And there's a point where the system becomes hard. And we believe that we want these two things to happen more or less at the same time. Because if you become ferromagnetic in the logical bits before, then it's difficult for you to rearrange when you enter the spin glass phase. Conversely, if you enter the spin glass phase when you're not correlated enough, you break the chains very easily and you generate basically something which is outside the embedded code space. So this gives you a prescription for which the optimal J ferromagnetic coupling needs to scale roughly as a square root of n. Now, the fitting is 0.6, but it gives you an idea. There are finite size effects all over the place. Okay, I will go fast in this because this is not really an annealing conference, but I just want to say that if you actually compute the expected time to solution of this problem, by optimizing, so at every size you choose the perfect ferromagnetic coupling for the problem, you have an exponential scaling which has a certain slope. And if you actually want to compare this with simulated annealing, what you do is you take simulated annealing, you take the logical problem, okay? So not embedded, not chimera, just you take Smelyanskiy, you optimize for the best annealing speed to make sure that you are as optimized as you want, and then you compare. And what you obtain is that, well, it's difficult to draw conclusions here, but you obtain a scaling which might be compatible, might be not, might be better, of course we'll see in the next iteration slides. But it's definitely something which is competitive from a practical standpoint. Okay, the best processor of playing supercomputer is compatible with D-Wave. Now the point is though that D-Wave has an handicap, okay, which simulated annealing doesn't. the fact that the calibration errors might actually encode a spoiled an Hamiltonian, which is noisy. Okay, and whenever I create a coupling, and I set this coupling to +1, I might actually set a coupling which is not exactly +1. And we can take advantage of knowing this fact by, okay, this just shows that simulated annealing correlates quite well with the D-Wave device. I don't want to go much into that. We can take advantage of that and try to see what simulated annealing how simulated annealing would perform if it had the noise also. Like we artificially introduce the same noise that we think D-Wave has, okay? And the noise comes from all sorts of places, like the crosstalk and the qubit non-ideality. And if we do this, I just want to mention that the larger the ferromagnetic coupling, defining the embedding, the larger is the noise. Because as I told you, I scale down the Hamiltonian. I have a maximum energy at which I can encode in the D-Wave machine. So the noise stays fixed. So the relative strength of the noise increases with the ferromagnetic coupling. So what you see here is how simulated annealing gets disadvantaged by the introduction of the noise. And since in our situation, simulated annealing correlates quite well with the D-Wave, we can extrapolate and say, well, we expect the D-Wave would also have, fortunately in this case, we would probably have a benefit for decreasing the noise, which is comparable to the disadvantage that we were able to compute in simulated annealing. So if we didn't have the noise, we could improve the scaling probably. This is what we could potentially say. And since I have a little time, I just want to mention another thing, that the noise level might be so bad that for large ferromagnetic coupling, you are sure that you don't solve the right Hamiltonian. And more specifically, you are sure that you're not looking at the ground state of the problem, meaning that you're sure the noise is sufficient that the real Hamiltonian you encode that doesn't share the ground state with the manifold of the ideal Hamiltonian you want. And if this is the case, then you're no longer playing the adiabatic game. You're no longer playing the slower you go, the better you are game, because you're not looking for the real ground state. You're looking for an excited state, which in the ideal Hamiltonian falls back to the ground state. And this we extrapolated, and we see that probably if the noise level doesn't go down, the next generation of device, we will be in such a situation for the fully connected graph. So that's the thing. Okay, I will spend the last 2 minutes just telling you that we have some indirect evidence, of course, that criticality plays a role, and I just showed to you the fact that there is an optimal J ferromagnetic coupling. This case is square root of n. But there is a question in the field of whether a chimera graph, such as the one implemented in the D-Wave machine, can actually encode hard problems. And it has been numerically demonstrated by Helmut Skatz-Graber that if you had a random instance of a spin glass defined on the chimera graph, so no ferromagnetic correlation, no embedding procedure, you would have defined a spin glass universality class whose temperature, critical temperature, is 0, and whose exponent of divergence of the correlation length is mu equal 4, which means that you are actually encoding problems which are classically easy, because the barriers of the spin glass space raises just at the end of the annealing in a simulated annealing procedure. So it's not surprising that you actually don't beat simulated annealing with this kind of things. Well, in Shelter hypothesis, we know that the spin glass space is defined at temperature. Correlation length is not really defined the same way, but there's a different universality class. And what we did is actually reproduce the same numerical technique with some modifications that we developed in order to deal with the chimera graphs embedded, and to check, I'll go fast because I don't have time, and to check one preliminary estimate of the spin glass temperature in our system. And what we find, again, we developed a Monte Carlo procedure for the simulated annealing that allows us to equilibrate in the presence of these ferromagnetic chains, which is not non-trivial. And what we found is that if you scale your observables by the appropriate parameter that allows you to make the energy extensive, you do have an intersection of the Binder ratio curves of the spin overlap configuration, for the people that know what I'm talking about. And this intersection is actually compatible visually for now with an exponent which is of the same order of the one that the Trento-Kirkpatrick theory would expect. And if you do increase the ferromagnetic coupling appropriately, our preliminary results shows that you converge to the value of the ferromagnetic temperature, of the spin glass temperature that the logical system would predict by the same numerical procedure. So it's a piece of evidence that we can encode, actually simulate on the D-wave machine, as well as any other annealing, through the embedding procedure, a universality class which is not necessarily the one of the native problems in the hardware. So maybe annealers one day will be probably good simulators of complex systems. And I conclude with this. Thank you.
So, from what I understood from your talk, I mean, suppose you have a very large spin model that you would like to simulate with a D-wave machine or with a quantum annealer, and of course you cannot solve it classically, so you cannot know which is the size of the gap. So your procedure will be to run the simulation for different speeds and make it slower and slower and analyze whether it converges to some definite
So in the situation I presented, I know the ground state because the sizes are sufficiently small.
I mean for larger systems.
Yeah, of course. So what I can do is just see the scale. No, we think that this is going exponentially. So at some point I don't have a guidance anymore, and what I can do is to run the predicted, extrapolated number of runtimes and reasonably believe that.
Trace the parameters and to see how the solution changes or something like that. To analyze for convergence of the final solution.
Oh well.
Optimization of this.
I mean, definitely you can compute the residual energy with respect to the best estimate you have. This you can do. Now, whether you can, I don't know if someone else has an opinion, but whether you can, in a very large system, run a procedure and be sure that you actually found the ground state,
I think you would look at convergence curves in a large system rather than on a time to solution.
You mentioned that the chimera graph you feel was terribly classically high. Do you have an alternative graph that is?
Well, the more connected it is, the better.
Sure, more quantitative?
We're investigating alternative architectures, but there are no like detailed study up to date for.
This is a good point. This is a possible study with architecture that should be better.
Isn't the first step to get rid of clusters and not have this like local fully connection and then just with a few wires go to another cluster? To have a non-trivial connection that not like local, like big global, not so much.
We don't know. This is not something that
Is there a limit or a cost to increasing the number of constraints on a linear graph? Is it possible to have a very large number of constraints and to have these constraints themselves not be linear?
Well, you have to fall back to a cuboform at the end, no? So you're talking about the the mapping procedure of an optimization problem. This is what constraint. This is what you mean, right? Okay. So there are several tricks to reduce the locality of a constraint, which is nonlinear, to a quadratic form, and so to be implemented. And I believe that maybe Alejandro mentioned some of them in his problem yesterday, but there are several tricks that you can apply. Mostly every polynomial constraint you can
So if I had like 20 or 30 simultaneously active constraints, would that be permitted in the suspect?
You're talking numbers which probably result in the number of qubits which cannot be embedded in this current generation device. But yes, the architecture allows to encode fully connected graph, so it allows to connect to code any qubit.
What are the errors or accuracy in megahertz of your H's and J's, like in D-Wave 2? This question could be for either of you guys. Do you know what those numbers are?
What we know is there is no publication of D-Wave on the subject. Okay, there has been several training internal. So what we can disclose is what they told us. Okay, and
is that in gigahertz? Is that 35 meg? No.
No. So these are relative magnitudes compared to a unit, which is 1, which is the max 3.2 gigahertz, which is the maximum energy of the system.
So it's 3% of that 3 gigahertz.
Okay. Roughly 5%. Now,
there's so many variants, as John said, there's so many variants of the variants, of which we understand some of them systematic, like a second order susceptibility, and we can understand and estimate that error. But some of them come from the low frequency noise, and we maybe can estimate it, maybe not, and there are many other things. So what we